Hi, we're given a list of numbers and we are to find the length of the longest consecutive subsequent where the values are either consistently increasing or decreasing or constant. Here's sample data. Now it might look like this sequence here is the longest one because the values here are constant and easy to spot. But this is actually only 2 steps because we go from here a 5 to a 5 and then from a 5 to a 5. Whereas over here we have 4 elements in a row that are consistently increasing, even though the increase is not consistent. So we would go from 1 to 2, and then 2 to 3, that's still increasing, 3 to 5, it's increasing. Okay, let's begin our lambda with p as argument, and we refer to the argument as omega because that's the rightmost letter of the Greek alphabet. And here, we are not actually interested in the values, we're interested in their relative sizes. So we can start by subtracting adjacent elements. So this does a 1 minus 2, and then 2 minus 3, and 3 minus 5. This might sound backwards, but it doesn't actually matter, because we're only interested in whether we're going up, or whether we're going down, or whether we're constant, and it doesn't matter if we flip around up and down. So here we can see that we're going up because the left element minus the right element is negative, and we're going up, and then we have 2 constant ones going down, and then up again, and then down, down. Okay, now we're not interested in how much we're going up or down. We're just interested in whether it's up or whether it's down. That is, we're interested in direction or the sign. So we can do that. And now we just want to find out whether adjacent elements in this indicator list are equal to each other. So we can use the same exact technique, but this time instead of using subtraction, we're using different from. So this tells us that the first element is the same, is not different from the second one. The second one not different from the third, and so on. That's these 3. And then we have 1 here, where the 0 is equal to the 0, so that's for this space over here, and so on. Okay, so how do we convert this to a list of lengths? One way to do it is by cutting this into pieces that begin with a 1. The only problem is the first one begins with a 0. It's missing kind of the 1 that the very first directional change is, of course, different from anything before it because there was nothing before it. So we can fix that by inserting a 1 in front. And now we can use the partition function to that takes exactly this kind of element, this kind of argument on the left, and cuts the data on the right into partitions that correspond to beginning with a 1 and then continuing with a 0. But here it doesn't actually matter what data it is we're cutting because we're only interested in the length. So we could just cut the data itself. And for that we have the self operator, also known as commute. So now we've cut into segments that begin with a 1, and then we can do the tally, which looks like a tally mark, on each. And this maps the tally over every segment. That gives us the length. Now we just need to find the largest one, which is a maximum reduction. And that gives us this solution, which is very nice and easy to understand. However, there's a principle in APL that if you want things to run fast, then you've got to stay flat. And as we can see here on the boxes, this result is not flat. It is a list of lists rather than a single list. So we could actually do this using a single list instead. A single flat list. Let's take this again. And this is the point where things go not flat, where we're doing so-called nested arrays. Let's go back and look at what we had here. All we want to do is find the distance from the beginning of one segment to the beginning of the next segment. So if we could find the indices of these ones and subtract them from each other, that would give the adjacent ones from each other, that would give us the segment length. The only thing missing, of course, is the ending point for the last one. So let's fix that by adding a 1 to the end. Now, the same symbol as we used before doesn't apply the concatenation with a single argument used on both sides. Rather, it flips the arguments around. So this becomes the left argument and this becomes the right argument. In effect, just as this was prepend a 1, this becomes append a 1. Okay, now we convert this Boolean indicator vector to a list of indices. These are indices of our ones. We can see that this one is in position 4, 5, and 6 over here, 7, and so on. And when we just need to subtract adjacent elements, but this time it is important which way we do it. So whereas this will give us the opposite of what we want, actually if we negate the 2 on the left, then it flips the subvectors before we apply the reduction on each subvector of length 2. So this flips the sign for us. And then the only thing that remains, of course, is taking the maximum. That works. Let's call this G. And to see what kind of difference in performance this makes, we need to have a little bit of a larger data set. So let's do a million numbers from 1 to 10. So this is a million reshaping a 10, so that's a lot of 10s, and then the question mark changes each 10 into a number between 1 and 10. We can look at the first 10 of them. Right. Now we can copy in the CMPX, compare execution utility from the defense workspace, and construct a couple of expressions that we want to compare in performance against each other. So we have F with the argument of Q, and we've got G with the argument of Q. And then we let that run for a little while. And we can see that with a million elements, we get a very significant speed up. Thank you for watching.